Welcome. This is the second in a series of presentations designed to provide guidance on specific technical aspects of the indicator methodology. In this session, we're looking at target values, and this concept is central to the indicator methodology and one of the aspects that challenged many countries during the first global data drive in 2017. This presentation is a companion to the technical guidance document that is available on the SDG indicator platform. This presentation is aimed at practitioners seeking further clarification on how to implement the methodology in their own country. It expands on the target value concept as presented in the step-by-step methodology. It outlines challenges to set meaningful target values. It suggests approaches to setting and or adapting existing target values from other jurisdictions. And it provides examples of target values that are used in different world regions. So to begin with, Indicator 632, it uses this target-based approach to classify water quality. This means that the measured values are compared to numerical values that represent good ambient water quality. Countries can set their own target values. And these target values, they can be either water quality standards that are defined by national legislation, or they may be derived from local knowledge about natural or baseline status of water bodies. But it's important, and we'll talk about this more, is that target values should serve to protect both ecosystem and human health. And on specificity, they can either be nationwide or more specific, down to the RBD or water body type level. And at the most specific, they can even be site specific. So what are target values? Physicochemical parameters, measuring those such as nutrient concentration or oxygen concentration, is one way to test whether water quality can be classified as either good or not. This is achieved by comparing the measured values against the numerical concentration limits that represent good ambient water quality, or these target values. So these target values are specific to each water quality parameter. So there may be one for oxygen, one for nitrogen, one for phosphorus, etc. And they aim to preserve that the ecosystem is preserved, or aiming to return it to its natural or near natural condition if possible. And the targets must also ensure that human health is not directly threatened if the water is consumed or used by humans. So to go more into detail on the human or ecosystem health, the process to define target values for classification of water bodies for Indicator 632 needs to consider both. An aquatic ecosystem in its natural condition is adapted to the water quality at that location. But this does not necessarily mean that the water quality is suitable to maintain human health. In certain cases, water quality in its natural state may be harmful and not suitable for direct human use without prior treatment. A good example is the nitrate concentrations, which can naturally exceeds the 50 milligrams per litre nitrate guideline concentration that is recommended by the WHO, the World Health Organization. And also naturally, water can have very high concentrations of arsenic or fluoride, which are toxic compounds. So in these cases, the natural water quality may be perfectly suited to the ecosystem, and the ecosystem may function perfectly at that location with this water quality. But human health may be at risk. But it's important to realise that the opposite may also be true. Target values that are based on human health alone may overlook the requirements of ecosystem health. Again, using the WHO drinking water standard, it may be safe for human consumption, but at that level of nitrate concentration, there may be consequences for the ecosystem. If this value was applied as a target value for a water body which has naturally very low background concentrations of nitrate, a slight elevation may lead to impairment of ecosystem function. A much lower ecosystem-based target that reflects the naturally low background nitrate level would be much better. In situations where target values for both ecosystem and human health are relevant, it's the most stringent that should be applied for indicator 632. There are some water bodies that may never achieve good ambient water quality classification, just simply because the natural water quality may never be suitable for human use without prior treatment. So water quality measurements for water bodies in a natural or a near natural condition that without any disturbance or exposed to very minimal disturbance from human sources. The water quality measurements should fall within ranges that reflect these natural conditions. For example, rivers may have high dissolved oxygen concentration, they may be low in nutrients, and have pH and conductivity values that are related to the geology of the area and the proximity to the coast, for example. So measuring repeatedly at the same location over time will produce a range of measurements for each parameter that can be defined statistically, within which the majority of all measurements should fall for that location under normal conditions. There could be diurnal, sort of daily or seasonal patterns in the data. For example, there may be a drop in dissolved phosphorus concentrations in temperate lakes during the summer when algal growth is greater. But there shouldn't be any upward or downward trend over time. All measurements should fall within this expected range. Target values are not the same as reference conditions, but they are closely related, and a target value should be based on knowledge of a reference condition. A target value may be derived from a known or an estimated reference condition, assuming that a slight deviation from the reference condition does not harm ecosystem function. Each water body is unique and it differs by certain natural characteristics, and these natural characteristics influence the natural water quality. The main factors here are shown in this table. So there's the location, so the latitude, the longitude, where it is, or maybe the depth below water for groundwaters. The geology, it's very important, the structure and the type of lithology underlying the catchment area. The climate, whether there's a lot of rain, not a lot of rain, the temperature, the prevailing wind direction, humidity, for example. The topography can have a difference, make a difference. The arrangement and shape of the physical landscape, whether it's steep or very flat, will have an impact. And also the biology. So the ecosystems within that catchment can play a part. So target values, they can be of one of three types. They can either, some parameters are best served by having upper target values, meaning that the value should not be exceeded and all measurements should be below that value. A good example is for nutrients. Often we like to see the nutrient measurement below a target value. Target values can also be a lower target value, meaning that all measured values should be above a certain concentration. For example, an often used target value for oxygen would be an 80% saturation, and all measurements, we hope, would be above that, so they'd be above the 80% concentration limit. And some parameters will have a target range, and this represents the normal acceptable upper and lower measurements of the limits. And pH is often used this way, so normally around neutral, so between 6 and 8 pH units, all measurements should be within that target range. Transboundary target values. So countries that share transboundary waters are encouraged to collaborate to set target values. And this is important because different target values in neighbouring countries may lead to a different classification of what is essentially the same water body and the same water quality. For example, if country A sets a more lenient target value than country B, this could lead to the same water quality being classified as good on one side of the international border and not good on the other. During the first global data drive in 2017, many countries chose to apply target values that applied to all water bodies of one type in the country. And this approach is more straightforward to apply than setting more specific targets. And it can be useful for certain parameters, especially dissolved oxygen and pH. But such broad targets do not take into account the natural diversity of water body, as mentioned in the previous two slides. And therefore, it may fail to protect the water quality. And this would therefore hinder progress towards target 6.3. And countries are encouraged to set more specific targets where they're needed and where resources and information to do so are available. So these next few slides describe the different levels of specificity of target values that can be applied. So at the broadest level is the national level. So this is a single numerical value or range for each of the water body types. So you'd have a single value for rivers, one for lakes, and a third for groundwaters for each of the parameters. At the next level, the RBD, or the reporting basin district level, this would be a set of target values which is defined specifically for each of the RBDs which have been defined in the country. The third level is a typology level. So for this to be possible, an exercise would need to be undertaken to categorise each of the water bodies within the country into certain categories or typologies. For example, a river's, it may be an upland compared to a lowland river, a wet river compared to one in an area which is more arid or less rainfall. Similarly for lakes, based on the typology of the lake, it may be the different trophic status of lakes could be used in this example. And for groundwaters also, it may not be appropriate to set the same target values for all groundwaters, but based on, for example, the type of aquifer may warrant a specific target value for one type and another target value for a different type of aquifer. At the water body level, this means a set of target values for each specific water body. And this approach might be needed to align with neighbouring countries, for example, for a transboundary water body. And at the most specific is at the monitoring station level. And in this example, there may be instances where right down at the monitoring station, it may need, for whatever reason, its own target value. So countries are encouraged to generate specific target values where the resources are available, and if there is a need to. If the water body is not protected, so if the national target values, for example, if they're not close enough to the natural condition of a water body, more specific target values are recommended, or the process of setting more specific target values is recommended, and therefore that will then help serve protect the water quality at that particular location. But as a general rule, national targets may be suitable for oxygen and pH, but for nitrogen and phosphorus and salinity, it may be more appropriate to set more specific targets. This table shows a good example from the Australian and New Zealand Environment and Conservation Council. From their water quality guidelines produced in 2000, the two countries were divided into broad geographical regions and then further divided based on climatic zones and administrative areas. So within each of these areas, a set of default guideline values were produced, and these can be used in place of if there's no specific local information of the different types. So you can see here in this example, there are, if you're looking at the TP, which is the total phosphorus concentrations, an upland river had as a recommended limit of 20 micrograms per litre, whereas a lowland river had a higher recommended target of around 50 micrograms per litre. As mentioned earlier, the natural trophic status is another way of categorising water bodies, and it may be relevant to set specific target values for the different water bodies of each based on their trophic status. And this example is from the Canadian guidelines, and for total phosphorus, for example, shown here, based on the different trophic status of lakes, a specific total phosphorus target value has been suggested. But this is based on natural eutrophication, and this is a process which takes centuries in lakes and is marked by a slow change in the productivity and there's an increase in biomass and sediment within the lake. This is not to be confused with artificial or cultural eutrophication, which is induced by human activities such as agriculture or wastewater effluents being pumped into water bodies, which accelerates this natural process and can lead to huge increases in plant biomass within a water body. In response to requests from countries to provide more complete guidance for global target values, for each of the core parameter groups, there's now a list of optional target values that can be used by countries. So defining numerical values that reflect good ambient water quality at the global scale is possible, but it's unlikely that these values are the most appropriate at the national or subnational scale. And adopting this one-size-fits-all approach, it fails to recognise the natural water quality variation. But the optional target values offered here can be used in the short term in the absence of any national target values. And they do also provide a benchmark against which national target values can be compared. These optional target values that are proposed, they derive from several sources, and countries with target values in place already are encouraged just to compare their own against these optional target values to see how they compare. And countries that currently do not have target values in place can adopt these in the short term until sufficient data are available to generate more relevant and therefore more appropriate target values. So this table lists the various targets for the core parameter groups for each of the water body types. And the following slides describe how each of these were derived. For oxygen, the optional target value range is between 80 and 120% saturation. And this is relevant for only surface waters only. And this figure shows some examples of the various jurisdictions for comparison. And the full reference list is included in the associated technical document. In this case, percent saturation rather than concentration, or a measurement in milligrams per litres, is suggested. And using a concentration of dissolved oxygen, such as 9 milligrams per litre, is not recommended because of the influence of temperature on oxygen saturation. So for salinity, naturally, freshwater concentrations for electrical conductivity can vary hugely between 10 and 1,000 microsiemens per centimetre, but there are many exceptions. The main drivers of natural conductivity are the lithology or the geology in the underlying catchment area, and the proximity to the coast. That can make a huge difference by deposition of sea salts onto the catchment area. Bedrock, which is more prone to weathering, will lead to greater dissolution of minerals in the rocks, leading to higher conductivity and salinity levels. And similarly, coastal catchments can have a higher conductivity because of the exposed to the greater atmospheric salt deposition. An optional target value of 500 microsiemens per centimetre is proposed in the absence of more specific information. And this value is lower than the majority of those reported in 2017, which was the median target value for that reporting period was 800. But in the absence of better information on water body reference conditions, it can be used in the interim as a target value. This target value agrees with the suggested published literature, and it also aligns with the global conductivity mean, which is about 220 microsiemens per centimetre. However, it's not suitable for water bodies for which the natural conductivity is much higher or much lower. But in the absence of any historical information, this value, it serves as an appropriate interim target value. But it is preferable and recommended that more specific targets are applied. Ideally, if there's sufficient historical information available, if it's possible to define maybe the 10th and 90th percentiles from the reference condition and then derive a target value based on those percentiles. For nitrogen, to fulfill the reporting requirements for nitrogen, countries can choose to report any form that they have data on, either inorganic or particulate forms. Inorganic, organic, or particulate or dissolved forms. The most commonly reported are either total nitrogen or total oxidized nitrogen, which is nitrate plus nitrite. Shown here are target values applied in various jurisdictions for surface waters, and based on these values, the optional target values are shown in this table here. So for rivers, a total nitrogen concentration of 700, and for lakes 500 micrograms of nitrogen per litre. And for oxidized nitrogen, or total oxidized nitrogen, for rivers 250, same for lakes, and same for groundwaters is recommended. But again, efforts to set target values which are based on local information is the better option. For the phosphorus parameter group, for indicator data collection, orthophosphate is the most straightforward form to measure, but many jurisdictions already include total phosphorus in their monitoring programs. Total phosphorus has an advantage in that it includes all forms of phosphorus that are present in the sample, and this may contain anything which is bound to particulate matter, for example, which could end up settling as sediment, and which could in the future serve as a phosphorus source if remobilised. So the extra analytical effort of measuring and reporting on total phosphorus is an advantage if possible. So shown here are the suggested concentrations for rivers and lakes for total phosphorus and orthophosphate or soluble reactive phosphorus. So for total phosphorus, 20 micrograms of phosphorus per litre for rivers and 10 micrograms of phosphorus for lakes. And SR, soluble reactive phosphorus or orthophosphate, is 10 micrograms and 5 micrograms of phosphorus for lakes. The acidification parameter group is most commonly reported on using the parameter pH. pH is one of the most widely measured ambient water quality parameters due to its influence on many biological and chemical processes, And the majority of freshwaters are naturally near neutral at pH 7, but they can be acidic or alkaline. For example, if they're downstream from a peat bog, they may be naturally acidic, or if the underlying geology is calcareous, they may naturally be alkaline. Shown here in this figure are various pH ranges used in different jurisdictions, and also shown are the target ranges suggested by the freshwater framework for freshwater ecosystem management, and a summary of the values reported in 2017. So based on all this information, the optional target range for pH is between 6 and 9 pH units. So in summary, target values are central to the SDG indicator methodology. They provide a straightforward method of water body classification. One limitation of this approach is that the classification assigned is very sensitive to the choice of target value used. The indicator score reported could be either more positive or negative than the reality. The optional target values suggested here provide a starting point for countries looking to develop new target values, and it provides a benchmark against which to compare existing target values. These do draw on global examples and published scientific literature, but their value in each national context can only be defined by each country. The target values used for indicator reporting are recorded by UNEP, and countries are asked to submit this information along with the indicator score. And this allows UNEP to keep track of the different approaches used by countries and to assess their comparability. Efforts to set more specific target values will lead in time to more robust classification of water bodies, and subsequently to more efficient allocation of resources to improve water quality. It will provide clearer and more reliable understanding of which water bodies are under threat. So thank you for listening. This final slide just shows you the link to the indicator support platform and also to the help desk.